Section: Introduction. In this section, we explore the significance of memory in learning, drawing inspiration from Samuel Johnson's assertion that attention is key to memory. We recognize that transformers, which rely on attention mechanisms, have become leading models in sequence tasks due to their ability to learn from context. These attention modules act like memory blocks, storing key value pairs and retrieving them based on similarities between queries and keys. However, this method has limitations, particularly in terms of time and memory usage, especially when dealing with large context windows in complex tasks like language modeling and video understanding. To address these scalability challenges, researchers have developed linear transformers that replace traditional methods with kernel functions, reducing memory usage. Yet, these models struggle to match the performance of standard transformers because they compress data into fixed-size states, which can hinder their effectiveness with very long contexts. Additionally, many existing architectures, including Hopfield networks and LSTMs, face difficulties in generalization and reasoning, which are essential for tackling real-world problems. We argue that an effective learning system should mirror the human brain structure, comprising distinct but interconnected modules responsible for various aspects of learning. Memory is a crucial element of this process, and we note that without a functional memory system, learning would be limited. Current models often define memory as a neural update from input and learning as acquiring useful memory for specific goals. We analyze recurrent neural networks, RNNs, and transformers in terms of their memory structures and update mechanisms. RNNs utilize a vector-valued memory, while transformers maintain a growing memory without compression. This leads us to question what constitutes an effective memory structure, the best memory update methods, and optimal retrieval processes. Furthermore, we recognize that human memory is complex, involving various systems like short-term and long-term memory, each with distinct functions. This complexity prompts us to consider how to design architectures that integrate different memory modules effectively. Lastly, we challenge the notion that a simple vector or matrix can adequately represent long-term memory, raising the question of whether a deeper memory module is necessary for effective long-term storage. Section Summary. In this section, we discuss the limitations of current transformer architectures in handling long contexts due to their quadratic complexity and the challenges faced by linear transformers in maintaining competitive performance. We propose that an effective learning paradigm should incorporate distinct yet interconnected memory modules, inspired by human memory systems, to enhance scalability, generalization, and the ability to learn from past experiences. Section C3 Contributions and Roadmap. In this section, we outline our contributions and roadmap. Our goal in this paper is to address 5 key questions by creating a long-term neural memory module that can learn to memorize effectively during testing. We introduce a deep neural long-term memory that functions as a meta and context model, learning to store data in its parameters at test time. Drawing inspiration from the human long-term memory system, we design this memory module to make surprising events more memorable. We assess the surprise of an input by analyzing the gradient of the neural network concerning the input in associative memory loss. To manage limited memory better, we propose a decay mechanism that considers the ratio of memory size to data surprise, leading to improved memory management. We demonstrate that this decay mechanism generalizes the forgetting mechanism found in modern recurrent models. Interestingly, we find that this mechanism aligns with optimizing a meta-neural network using mini-batch gradient descent, momentum, and weight decay. By enhancing mini-batch gradient descent with more matrix multiplication operations, we present a fast and parallelizable algorithm for training our deep neural long-term memory. After establishing the long-term neural memory, we address how to effectively integrate this memory into a deep learning architecture. We introduce Titans, a family of deep models featuring 3 components. 1. Core. This module includes short-term memory and manages the primary data processing flow using attention with a limited window size. 2. Long-term memory. This branch is our neural long-term memory module responsible for retaining long-term information. 3. Persistent memory. This consists of learnable parameters that are independent of specific data but encode knowledge about a task. As a proof of concept, we present three variants of Titans, incorporating memory as I, a context, E, a layer, and E, a gated branch. We conduct experimental evaluations across various tasks, including language modeling, common sense reasoning, recall-intensive tasks, time series forecasting, and DNA modeling. Our results show that the Titan architecture outperforms all modern recurrent models and their hybrid variants across a wide range of benchmarks. Additionally, Titans surpass transformers with the same context window and demonstrate competitive performance with transformers that utilize the entire context, achieving this while scaling beyond a context window size of 2 million. In the preliminaries, we clarify the notation and background concepts used throughout the paper. We denote the input as a matrix, the neural memory module as M, and the components of the attention mechanism as Q, K, and V. We also refer to segments of the sequence using specific notation. We discuss the backgrounds for attention and its efficient variants, followed by a review of modern linear recurrent neural networks, ultimately motivating our design of Titans. In the background section, we explain that transformers, which are foundational for many deep learning models, rely on the attention mechanism. We describe how causal attention computes output based on input-dependent matrices, noting that this process can be memory-intensive for longer sequences. To enhance memory efficiency and throughput, various studies have explored efficient attention mechanisms, particularly linear attentions, which replace the standard softmax with alternative kernel functions, allowing for more efficient computations. We also discuss modern linear models and their memory perspective, viewing the hidden state of recurrent neural networks as a memory unit. We highlight the importance of read and write operations in this context and address the challenges of memory overflow when dealing with long context data. We explore two main directions for improvement: adding forgetting mechanisms and enhancing write operations to manage memory more effectively. Finally, we emphasize that memory has always been central to neural network designs. We reference the concept of linear layers as associative memory systems and discuss various learning rules that have been applied to fast-weight programs. However, we note that many existing models overlook the flow of tokens in sequences and often lack forgetting mechanisms, leading to suboptimal memory management. We will further elaborate on the connections between our architectures and recent models in the appendix. Section Summary. In this section, we outline our approach to developing a long-term neural memory module that learns to memorize data at test time, inspired by human memory systems, and introduce the Titans architecture, which integrates short-term, long-term, and persistent memory components. We also present experimental results demonstrating that Titans outperform existing models across various tasks while effectively managing memory through a novel decay mechanism. Section: Learning to memorize at test time. In this section, we introduce a neural long-term memory module designed to help our model learn, forget, and retrieve information effectively during testing. We begin by discussing the motivation and design of this memory module. Next, we explore how our architecture can benefit from fast and parallel training. Finally, we enhance our architecture with a persistent memory module that uses learnable but data-independent parameters to capture meta-information about the task. To create a neural long-term memory module, we need a model that can encode past experiences into its parameters. For instance, large language models, LLMs, have been shown to memorize their training data. However, memorization is often seen as a drawback because it can hinder generalization, raise privacy issues, and lead to poor performance on unseen data. We propose an online meta model that learns how to memorize and forget data during testing, allowing for better generalization without overfitting to the training data. Our approach treats the training of long-term memory as an online learning problem, where we aim to compress past information into the parameters of our memory module. We draw inspiration from human memory, where surprising events are more memorable. We define surprise for our model as the gradient with respect to the input. A larger gradient indicates that the input is significantly different from past data. However, this surprise metric can overlook important information that follows a surprising event. To address this, we break the surprise metric into two components: past surprise, which captures recent surprises, and momentary surprise, which reflects the surprise of incoming data. This formulation resembles gradient descent with momentum, where the momentum acts as a memory of surprise over time. Our surprise metric is based on a loss function that guides our memory module to perform effectively during testing. We focus on associative memory, where we store past data as pairs of keys and values. Given an input, we project it into a key and value using linear layers. Our memory module learns the associations between these keys and values by optimizing a defined loss function. When dealing with large sequences, it is essential to manage which past information to forget. We implement an adaptive forgetting mechanism that allows the memory to discard unnecessary information, optimizing its limited capacity. This mechanism uses a gating parameter to control how much information should be forgotten, enabling flexible updates to the memory. We utilize simple multi-layer perceptrons, MLPs, as the architecture for our long-term memory, focusing on motivating the design and integration of this memory into our framework. Our approach opens new avenues for developing more effective neural architectures for data memorization. We also discuss the potential of using deep memory modules, which can be more expressive than linear models. Finally, we address how to retrieve information from the memory. We can simply perform a forward pass without updating the weights to retrieve memories corresponding to a query. Section Summary. In this section, we present a neural long-term memory module that enables models to learn, forget, and retrieve information at test time, addressing the challenges of memorization and generalization. We introduce a surprise-based metric to optimize memory updates, implement an adaptive forgetting mechanism, and explore the architecture's potential for effective data memorization and retrieval. Section: How to parallelize the long-term memory training. In this section, we discuss how to parallelize the training of our long-term memory module. We view this module as training a meta-model by optimizing a specific loss function using gradient descent with momentum and weight decay. Theoretically, this training requires a number of floating point operations proportional to the sequence length. However, to effectively utilize hardware accelerators like TPUs and GPUs, we need to parallelize the training and use more matrix multiplications. We can reformulate the calculation of weights in the inner loop with mini-batch gradient descent, a data-dependent learning rate, and weight decay to rely solely on matrix multiplications and summations. Building on previous work, we can split the sequence into chunks and express mini-batch gradient descent accordingly. For simplicity, we focus on the first chunk, where we can define certain parameters and store them for each chunk, reducing memory usage. Next, we incorporate the momentum term into our gradient descent process. We can compute all momentum values simultaneously, allowing us to use parallel associative scans to calculate hidden states efficiently. Instead of making parameters dependent on individual inputs, we can make them functions of their respective chunks. While this may reduce expressive power, it can speed up training. In our experiments, we initially use input-dependent parameters, but we see potential in chunk-based parameters for future work. We also introduce the concept of persistent memory, which acts as contextual memory. This memory relies on both input-dependent and input-independent parameters to store task-related knowledge. We append learnable parameters to the start of our sequence to enhance this memory. From a memory perspective, effective systems need both types of parameters to capture task knowledge. In terms of feed-forward networks, we note that certain layers can function similarly to attention weights when they are input-independent. Finally, from a technical standpoint, using learnable parameters at the beginning of the sequence can help mitigate biases in attention weights, improving overall performance. Section Summary. In this section, we describe how to parallelize the training of our long-term memory module by reformulating the mini-batch gradient descent process to utilize matrix multiplications, which enhances efficiency on hardware accelerators. We also introduce a persistent memory component that incorporates learnable, input-independent parameters to improve task knowledge representation and mitigate performance issues related to attention biases in sequence processing. Section: How to incorporate memory. In this section, we address the important question of how to effectively integrate our designed neural memory into a deep learning architecture. We previously discussed that the K and V matrices in transformers can be seen as an associative memory block, functioning as short-term memory due to their ability to model dependencies within a limited context window. In contrast, our neural memory continuously learns from data and stores it in its weights, serving as long-term memory. To tackle the integration challenge, we propose 3 different variants of Titans. Our experiments will demonstrate that each variant has its own strengths and weaknesses, revealing a trade-off between efficiency and effectiveness in handling very long contexts. In our first architecture design, we treat memory as context for current information. We take a long sequence and divide it into fixed-size segments. For each incoming segment, we consider it the current context and its preceding segment as historical information. We use the state of long-term memory before the current segment to retrieve relevant past information. This is done by using the current segment as a query to access the long-term memory. We then combine this historical information with our persistent memory parameters as input to the attention module. The attention map structure is illustrated in our figures. We update the long-term memory module with the output for the next segment, ensuring that the weights of the memory are adjusted during the forward pass. This architecture has several advantages. First, the attention mechanism allows us to determine if long-term memory information is necessary based on the current data. Second, it helps the memory retain only useful information, preventing memory overflow by filtering out irrelevant tokens. Third, during testing, the persistent memory parameters remain fixed, while the attention module acts as an in-context learner, and the long-term memory continues to learn and memorize information. In our next variant, we introduce a gated memory design. Here, we directly use the input data to update long-term memory in one branch, while in another branch, we apply sliding window attention. Unlike the previous design, we do not segment the input data. We denote the final output of the memory after processing all tokens as a function of the input. In this setup, sliding window attention serves as precise short-term memory, while the neural memory acts as a fading memory for the model. Our final variant employs neural memory as a layer within a deep neural network, a more common approach in the literature. In this design, we stack recurrent models with either full or sliding window attention. However, this design has a limitation. The model's power is constrained by each layer, preventing it from fully leveraging the complementary processing capabilities of attention and neural memory. We also explore a simpler variant of this architecture, treating the neural memory module as a sequence model without any attention. We believe that each part of the memory system should function independently, even if other components are disrupted. Thus, our long-term memory module remains effective even without short-term memory. We refer to this variant as LMM or Titans in our experiments, and we provide further discussions on its connection to modern recurrent models in our appendix. Section Summary. In this section, we explore how to effectively integrate neural memory into deep learning architectures by proposing 3 variants of Titans, each balancing efficiency and effectiveness for long context processing. We discuss designs that treat memory as context, utilize gated memory mechanisms, and implement memory as a layer, highlighting their respective advantages in managing historical and current information. Section: Architectural Details. In this section, we outline the architectural details of our model. For clarity, we will not delve into specific implementation aspects such as residual connections, gating with linear layers, or normalization. We utilize residual connections in all blocks. Our model employs the CLU activation function for calculating queries, keys, and values, and we normalize these using the 2 norm. We incorporate a one-dimensional depthwise separable convolution layer after each projection of queries, keys, and values, following recent advancements in linear recurrent models. While these convolutions do not drastically change performance, they do enhance it and are computationally efficient. We also adopt normalization and gating with a linear layer before the final output projection, similar to recent architectures. Unlike transformers and other models that are limited in their capabilities, our titans can tackle more complex problems, making them theoretically more expressive in state tracking tasks. Next, we evaluate the performance of titans and their variants across various tasks, including language modeling, common sense reasoning, and time series forecasting. We aim to answer several empirical questions regarding their performance compared to baselines, the actual context length, scaling with context length, the impact of memory depth on performance and efficiency, and the contribution of each component to overall performance. In our experiments, we focus on three variants of titans: memory as a context, MAC, memory as a gate, MAG, and memory as a layer, MAL, along with a standalone neural memory module. We define learning as the process of acquiring effective memory, and we expect our long-term memory to learn from data even without attention. We evaluate these models at 4 parameter scales: 170 million, 340 million, 400 million, and 760 million. The first 3 are trained on 15 billion tokens from the Fine Web Edu dataset, while the last one is trained on 30 billion tokens. We compare our models against state-of-the-art linear recurrent models, transformers, and hybrid models in various tasks. In language tasks, we benchmark against models like Transformer++, RetNets, and gated linear attention. For needle-in-haystack tasks, we include comparisons with GPT-4 and Llama 3 with RAG. In time series tasks, we evaluate against Mamba-based and Transformer-based models. For training, we follow the procedure outlined in recent literature, using the Llama 2 tokenizer with a vocabulary size of 32,000 and a training length of 4,000 tokens. We employ the Atom W optimizer with a learning rate of 4 × 10 to the power of -4, a cosine annealing schedule, a batch size of 500,000 tokens, and a weight decay of 0.1. Section Summary. In this section, we outline the architectural details of our Titans models, highlighting the use of residual connections, CLU activation, and 1D depthwise separable convolutions to enhance performance and efficiency. We also describe our experimental setup, comparing Titans with various state-of-the-art models across multiple tasks, while detailing our training procedures and the specific variants of Titans we evaluated. Section: Language Modeling. In this section, we focus on perplexity in language modeling and common sense reasoning tasks. We report results for Titans variants and baselines with sizes of 340 million, 400 million, and 760 million parameters. Among non-hybrid models, including Transformer++, our neural memory module shows the best performance in both perplexity and accuracy. When we compare our neural memory module to TTT, another gradient-based recurrent model, we highlight the significance of our weight decay and momentum. Weight decay acts as a mechanism to forget past data when necessary, while momentum helps us manage memory by adding to the surprise metric. Although some baselines, like Mamba and gated DeltaNet, also use gating mechanisms, our neural memory module's superior performance emphasizes the importance of our surprise mechanism and deep, nonlinear memory, which we discuss further in a later section. When comparing hybrid models, we find that all 3 Titans variants, MAC, MAG, and MAL, outperform both Samba and gated DeltaNet H2. We attribute the success of Titans, MAL, to the strength of the neural memory module, as the architecture and attention used are consistent across models. Between Titans, MAG, and MAC, we observe that while their performances are similar, MAC excels in handling longer dependencies. Interestingly, both MAG and MAC outperform the MAL variant, which we believe is due to the architectural design of these models. This finding is crucial since most current hybrid models in the literature use a MAL-style combination of recurrent models and attention. Next, we address the needle in a haystack (NIA) task, which assesses the effective context length of models. In this task, we evaluate our model's ability to retrieve specific information from lengthy distractor texts. We utilize the single NIA task from the ruler benchmark and assess titans and baselines on sequences of lengths 2000, 4000, 8000, and 16,000. Our neural memory module consistently outperforms the baselines across all tasks. We attribute this success to three main differences. First, our neural memory effectively manages memory capacity through momentum and forgetting mechanisms, maintaining performance as sequence length increases. Second, titans possess deep nonlinear memory, leading to better memory management compared to Mamba 2, which struggles with longer sequences. And third, while DeltaNet can remove memory, it lacks a true forgetting mechanism. In the Bobby Long benchmark, we explore a more challenging task where the model must reason across facts in very long documents. We follow the original experimental setup and training process, using both a few-shot setting with large pre-trained models and a fine-tuning setting for the Mac variant of Titans. In the few-shot setting, we find that Titans outperform all baselines, including large models like GPT-4, despite having significantly fewer parameters. In the fine-tuning setup, we compare a small fine-tuned version of Titans, Mac, with various models, including smaller models and extremely large ones. Titans again outperform all models, including the large GPT-4, primarily due to their powerful memory capabilities. Unlike RMT, which compresses historical data into a small vector, Titans can encode past information directly into the model's parameters. Notably, even augmenting the Llama 3.1-8b model with retrieval augmented generation does not match Titan's performance, despite Titans having around 70 times fewer parameters. Section Summary. In this section, we demonstrate that our neural memory module outperforms various baselines in language modeling and common sense reasoning tasks, particularly excelling in handling longer sequences due to its effective memory management strategies, including weight decay and momentum. Additionally, our Titans models consistently outperform both smaller and larger models, including GPT-4, in challenging benchmarks, showcasing the advantages of our deep nonlinear memory architecture. Section: The Effect of Deep Memory. In this section, we evaluate the impact of deep memory on both training time and model performance. We examine various versions of our neural memory module with memory depths of 1 to 4. We use Mamba as a baseline for comparison and ensure all models undergo the same training process on a subset of the PILE dataset. We present the perplexity of our models and baselines based on sequence length. Notably, as we increase the memory depth, the model consistently achieves better perplexity across all sequence lengths. Additionally, deeper memory modules show greater resilience to sequence length when the model has fewer parameters. As the number of parameters increases, all models perform better on longer sequences. We also assess how memory depth affects training throughput, which is the number of tokens processed per second, again based on sequence length. All models demonstrate a linear scaling with context length, meaning the tokens per second remain constant as sequence length changes. However, we observe that deeper memory leads to slower training, indicating a trade-off between effectiveness and efficiency. To demonstrate the effectiveness of our memory module in broader tasks, we evaluate its performance in time series forecasting using the Simba framework, replacing its Mamba module with our neural memory. Our results on standard time series forecasting datasets show that our neural memory outperforms all baseline models, including those based on Mamba, linear methods, and transformers. Next, we explore the capabilities of our models beyond natural language by testing them on DNA modeling tasks. We evaluate pre-trained models on downstream genomics tasks, following the experimental setups from previous studies. Our findings indicate that our models are competitive with state-of-the-art architectures across various genomics tasks. In terms of efficiency, we compare our neural memory and Titans with leading sequence models. We report the training throughput for different sequence lengths multiplied by batch size. Our memory module is slightly slower than Mamba 2 and gated DeltaNet due to its deeper memory and more complex memory update processes. Interestingly, Titans are faster than both the baselines and our memory module, primarily because of the highly optimized kernel used in their implementation. Finally, we conduct ablation studies to analyze different architectural choices in Titans. We start with our neural memory module as a base model and modify one component at a time, such as replacing deep memory with linear memory and removing convolution, momentum, weight decay, and persistent memory. The results show that all components positively impact performance, with the most significant contributions coming from weight decay, momentum, convolution, and persistent memory. To assess the effect of architectural design, we compare the performance of 3 variants of Titans across language modeling, common sense reasoning, and long context tasks. Our findings reveal that 2 models perform similarly in language modeling and common sense reasoning, while one model excels in long context tasks. Overall, these results highlight the trade-off between fast training and a more expressive design.